In previous lecture, we defined maximum flow problem and studied the Fulkerson algorithm for finding maximum flow, and we found the time complexity. We derived the time complexity of the algorithm. So it is big O of C times number of edges, where C is the outgoing capacity from S, sum of all outgoing capacities from S. Now the remaining task is to prove that actually Fulkerson algorithms returns the maximum flow. So for this we require this one theorem that is called Max-Flow Min-Cut Theorem. So which says that maximum flow on a flow network is same as the minimum cut of the flow network. So first we define the minimum cut, then we will prove our Max-Flow Min-Cut Theorem. So this will prove that. So in the process we will prove that Fulkerson algorithm actually gives the maximum flow, and also we can modify it to find the minimum cut of the flow network.
So what do you mean by minimum cut?
Minimum cut we will define. So now we define ST cut. So ST cut we define it as a partition AB of the vertex set V such that S belongs to A and T belongs to B. This is called ST cut. Now we define capacity of the cut. So after defining the ST cut, we define capacity. So we define this as capacity of a cut, call it AB. We define this as sum of capacities of all edges out of A. So we define this as CAB, capacity of the cut, is equal to sum of all capacities CE, where E out of A. So the edges which are going out from the boundary of A, we add the capacities, corresponding capacities, and this we define as capacity of the cut CAB. Cut, capacity of the cut. So cut, here we have defined ST cut. Just partition the vertex set into A and B such that S belongs to A, T belongs to B. This is definition of a cut. Next we define capacity of the cut. So capacity of the cut we define simply as the sum of all, just consider all outgoing edges from A, make a boundary of A, see which edges are going out of A, simply add the capacities. So this we define capacity of the cut AB. Now let F be any ST flow. Let F be any ST flow and AB any ST cut. So now what we'll do is we'll get a relation between value of the flow and the cut. So for Max-Flow Min-Cut Theorem, we will show that the value of the flow is upper bounded by the capacity of the cut, so that we get Max-Flow Min-Cut Theorem. So we start with F, which is any ST flow. We will compare value of this flow with the capacity of this cut, and let AB be any ST cut. So we will compare the two. We will compare VF, compare VF with capacity of the cut AB. For any cut AB and any flow F, ST flow, we will compare this So just consider what is value of the flow. So according to our previous definitions, value of the flow is relative to this cut. So it is simply flow out of A minus flow in of A. So take any subset of vertices, it cannot conserve or consume except for the S and T vertices. So here S belongs to A, so it is generator of the flow. So just compare the difference, flow going out of A, flow coming into A. So the difference should be exactly the amount of flow that is generated at S. So value of the flow. So value of the flow is F out of A minus F in of A. And also using the similar definition, we also have this value of the flow. You will get same flow whether you take S or you take any set of vertices. Yes. So value of the flow is actually F out A minus F in A for any A. So in particular, we can also choose this S. This is also an ST cut. So as a special case, we get value of the flow as F out of S, because there is nothing flow into S. This is because we have F in of S is 0. So you can also write like this minus F in of S, because F in of S is 0. So these are two equivalent definitions. Value of the flow, either you can take, actually it is F out of S, you can also write it as F out of S minus F in of S for source vertex, and also for any cut AB where S is in A, F out of A minus F in of A.
So that would also be equal to the flow generated
Yes,
at the source.
Same flow. Value of the flow, both cases are same. So let this be first equation. We will compare the equations. Now take any V. Take any vertex V belonging to A minus S. So except for the source vertex, just apply the capacity condition. No, not capacity, conservation condition. Apply conservation condition. Flow is conserved at V. So F out, the difference of F out and F in is 0. So we write F out of V minus F in of V. This is 0. Call this equation 2. Now just using 1 and 2, what we get? Value of the flow. Value of the flow set of all V is in A, V is in A, F out of V minus F in of V. So just we have combined, call this equation 3. So second equation says F out of V minus F in of V is 0 for all V other than S, and equation 1 says F out of S minus F in of S is Vf, value of the flow. Just add everything, so we get this equation. Value of the flow is a simplified equation. We get sum of all V in A including S and also vertices which are not S, F out of V minus F in of V. So this is third equation.
So in this case, we should also exclude T.
T is already excluded. Just see, the definition of cut says S belongs to A, T belongs to B. We are focusing only on A, so there is no question of T. So now we have this simplified equation. Value of the flow is F out of V minus F in of V. sum of all over V is in A, where S is in A and AB is a cut. Now we identify 4 types of edges. 4 types of edges we identify and consider each case one by one. 4 types of edges are there. We consider each case one by one. So first are edges within A. Edges within A. So here we have the boundary between A and B. This is A and let it be V1 to V2. Call this edge E. So just see what is contribution of this edge. F out of V1 and here it is F in of V2. So in this sum, we are considering this sum where V varies over all the vertices within A. We consider contribution of each edge, how much it contributes. So a single edge which is within A means V1 to V2, both V1 and V2 are within A. So how much we this is how much there is a contribution. So contribution in this third summation, contribution in equation 3. So here it is Fe. So Fe and we have this F out minus F in. So each contribution is Fe. So here contribution of F out of V1 is plus Fe, and since we have this minus sign, we have minus Fe. So net effect is 0. Net effect is 0 when we have edges within A. Similarly, consider edges within B. Second possibility is we have edges within B. So edges within B is very simple. We have a cut between A and B. We have a boundary, and now this V1 to V2. So here no contribution. So we are considering all possible edges. So for this edge there is no contribution, because when edges are within B, both these vertices they are not in A. So but the sum is over all V in A. So there is no contribution. So contribution we can say is 0. Next, similarly, crossing edges we consider between A and B. Third possibility is edges from A to B. So here we have A, B, this boundary, V1 is in A, V2 is in B, crossing edge. So here we have only a single contribution. This V2 contribution will not have, we will have only this V1, and as F out. F out of V1 contribution is plus Fe, because F out has positive sign. So this much is the contribution. Now similarly consider last possibility. Last possibility is just the reverse, edges from B to A. So this is the just opposite. We have the cut A and B. This is the boundary. V1 to V2 we have edge. So now here we have contribution, this F in of V2 in the third summation. So because F in has negative sign, so here contribution is minus Fe. Yes, just see this consider this third equation. Value of the flow is sum over all V is in A, F out of V minus F in V. V should belong to A. So, we consider only vertices which belong to A, not to B. And here F out has positive sign, F in has negative sign. So, whenever we get F out, it will be plus Fe. Whenever we get F in, it will be minus Fe. So, first case edges within A. So, we have both will contribute, plus Fe minus Fe, net effect is 0. Edges within B, no contribution because these are not counted in the sum. Third, edges from A to B, no contribution from V2. From V1 we have plus Fe because we have F out. Now edges from B to A, we have only incoming F in V2 and it has negative sign, so we have minus Fe. So now what we observe, using 3 and this above observations. So we start with value of the flow, sum of all V is in A, F out of V minus F in of V. So this we can write. So contribution we can identify. Positive sign when it is out, negative sign when it is in. So the same summation we can simplify this as sum of all, just write simply E out of A, E out of A Fe minus sum of all E into A Fe. So here we have further simplified our equation. Now what is this quantity? These two quantities, by definition these are F out of A minus F in of A. This is value of the flow. So here actually we have proved our earlier claim. Value of the flow is F out of A minus F in of A. So we started with this, that value of flow should be F out of A minus F in of A. So this is the proof why value of the flow is actually F out of A minus F in of A for any cut AB where S is in A. So this is a very simple equation. Now we will get upper bound. So before getting the upper bound, just take a very simple example. How example of this equation with a simple example. So we take our same earlier example, flow network SU V and T. Capacities are 20, 10, 30, 10 and 20. So flow I will show in circle to save space. 20, 10, then again here 10, here also 10, and here we have 20. So now here we find there are 4 possible ST cuts and we verify our equation. So 4 possible ST cuts. So simplest case is S itself is a cut. So A is S, B is UVT. First possibility we consider set A is S or set is B is UVT. Now we compute F out of A and F in of A. F out of A is equal to we compute flow out of this, just take this boundary, flow out is 20 plus 10 is 30, 20 plus 10 is 30. Similarly, flow into E. So into E, again we make the boundary, there is no flow in, so it is 0. So value of the flow, so this is the trivial most simple case. Value of the flow is defined as flow out of S, it is actually 30, and here you can observe the difference is 30. So in each case you will get the difference as 30. Second possibility we take, SU is A, VT is B. Second possibility we take, A is SU, B is VT. We compute both. F out of A is equal to, now make a boundary around S and U, just consider flow out of SU set. So we have 3 flows, 10, 10 and 10. 3 times 10 we get 30. So here it is 10 plus 10 plus 10 is 30. Now flow in of A. So there is no flow in, it is 0. So here also the difference is 30. Third possibility we take, for third possibility just different, combine S with V, U with T. Now what is flow out of A? So just consider outgoing edges from the boundary. So we have one is 20, this is incoming, this is outgoing. 20 plus 20. So F out of A. So third possibility we have, A is SV, B is UT, and flow out we have computed of A is 20 plus 20 is 40. Flow in, so there is incoming flow of 10 value. Flow in of A is 10. So here again we can verify the difference is 30. Now last possibility is take SUV in A, T alone in B. So this case flow going out, there is no flow in. There is no flow in. Flow going out is 10 plus 20, 30. So this fourth possibility, A is SUV, B is T, flow out of A is 10 plus 20 is 30. There is no flow in of A is 0. So in each case you can verify value of the flow is flow out of A minus flow into A, where AB is a cut, S is in A. So next we proceed for this upper bound on the flow. So we take any flow F, any cut AB, ST cut, and we get upper bound of the flow S, value of the cut.
Sir, how you are making that clear, like SV, SU and SU?
Here we are considering all possible ST cut. ST cut means set A will have S, set B will have T. How many possibilities are there? First, A can have only S, second, and B UVT. Second possibility, A can have SU and B VT. Third is A can have SV, B can have UT. Third, A can have SUV and B can have T. Only 4 possibilities. So in each case I have shown that value of the flow is flow out of A minus flow into A. So now we can easily derive the upper bound for any flow and any cut, ST cut. So let F be any ST flow and A be any ST cut. Then value of the flow is upper bounded by capacity of the cut AB. So we use the same formula that we derived that value of the flow is F out of A minus F in of A in deriving this upper bound. So we start with value of the flow, just write it as F out of A minus F in of A upper bounded by, just ignore the negative term, write this as F out of A upper bounded by, here just apply the capacity condition. So flow out of A, it is upper bounded by the capacity out of A. So just write this as sum of all E out of A Fe. This is, so this is actually just writing the expression E out of A Fe. Flow out of A is E out of A Fe. Now just here we apply the capacity condition. So Fe is upper bounded by the capacity because it is a flow. So upper bounded by Ce E out of A. And this is the definition of capacity of the cut AB. So we have derived that value of any flow is upper bounded by capacity of any cut. Here we are free to choose any flow and free to choose any cut. So this is true in general. So what we observe from this, that value of flow is upper bounded by capacity of any cut. So this holds for any pair of flow F and cut AB. So out of this pair, what we do is, this also holds when we take maximum flow. Just take max flow on the left side and min cut on the right side. So this also implies that, call this F star and this A star B star. The min cut is A star B star and max flow is F star. So this also says that this implies value of max flow is upper bounded by value of min cut. So but we'll prove extra that actually if we compare maximum flow with minimum cut, actually they are equal. So we'll prove that. We'll prove the Max-Flow Min-Cut Theorem. Max-Flow Min-Cut Theorem. So this says that max flow equal to min cut, means V of F star is actually same as capacity of the min cut. So maximum flow is equal to minimum cut. So this will prove. So the same thing, this statement we can also verify with our example. The 4 possible cuts that we have seen. So value of the flow we know is 30. What is size of the cut? In each case we will compute the size of the cut also. So first consider first possibility. Size of the cut is capacity out of A. Capacity out is 20 and 30. So we can also write here CAB is actually 30. So value of the flow 30 is upper bounded by 30. Second case we consider SU. So for SU, what is capacity of the cut? Capacity out of A, it is 10 plus 30 plus 10. So 50. So second case it is 50. Here CAB is 50. Again it is greater than 30. Third possibility we consider SV. Now what is capacity out of A? First is 20, then second is 20, it is 40. So third case it is 40. Capacity of AB is 40. So here also 40 is greater than 30. Now last possibility, this, what is the cut? Capacity out 10 plus 20 is 30. Fourth case also, CAB is 30. Now what is the minimum cut here? Minimum cut is this.
Can you please recheck the
Yes.
CAB of second case?
Second case, I will check. Second case, when SU,
Yes.
capacity out 10, 30, 10, 50 we get. So minimum cut here we find, minimum cut is 30. In two cases we are getting 30. So actually we are getting max flow is also 30, min cut is also 30. Max flow equal to min flow. No, max flow is equal to min cut we are getting. So now we'll prove the equality, the Max-Flow Min-Cut Theorem. So we'll prove proof of Max-Flow Min-Cut Theorem. We'll prove this. So here we have a very simple observation we'll make. So just remember the Ford-Fulkerson algorithm. We start with the graph G. We start with flow equal to 0. It is a valid flow. We make the residual graph, find ST path, augment the path, make the residual graph and continue like this until we are unable to find ST path. So last step, we do not have any ST path. So that time, so we'll prove that when the algorithm halts, actually we are getting maximum flow and minimum cut. So this observation will apply. So we start with F using Ford-Fulkerson algorithm. Just consider in Ford-Fulkerson algorithm, just consider let F the final flow, ST flow. So this implies the algorithm halts when there is no ST path. So it implies there is no ST path in the residual graph GF. So now we'll prove that there exists an ST cut. We'll prove that there exists an ST cut. Call it A star B star, for which value of the flow is same as, so better we call it F star according to our earlier notation. Call this F star. Value of the flow is capacity of A star B star. So we just will prove that value of the flow is same as capacity of the cut. So this in itself will prove that the value of the flow is maximum flow and capacity of the cut is minimum cut, because equality we get. So equality is the best possible we can get, otherwise we will have strict inequality. So equality will in itself will prove that flow is maximum and also cut is minimum. So we need to prove only this, value of the flow is same as capacity of the cut. Now how we define the cut? So definition of cut is very simple. So A star we include all vertices reachable from S. So let A star denote the set of all nodes V in the vertex set for which there is an SV path in GF star. Here also just call it GF star. So A we define as all reachable vertices from S in GF star. So that we define as A star, and remaining B star we define just its complement V minus A star. So two things now we have to prove. First, that it actually makes a cut. So cut we can easily see. So for two things we have to prove. First, that this A star B star is an ST cut. Second thing, we have to prove that value of F star is same as capacity of the cut A star B star. So first thing, we observe that this is A star B star is a partition of V and S belongs to A star. So for one, just consider A star B star is a partition of V, and how we define A star is such that S belongs to A star. So A star includes all vertices reachable from S, so S will belong to A star, and also that T does not belongs to A star. Why? Because there is no ST path. This is our assumption. There is no ST path, so T cannot belong to A star. So it implies T belongs to B star. So A star B star is actually an ST cut. So we have proved the first part of the result that we want to prove, that A star B star is actually an ST cut. Now we'll prove that value of the flow is same as capacity of the cut. So here once again just consider the same case. In GF, what is happening? Consider the partition of A star and B star in GF star. Just consider this graph. Here we have partition, left we have A star, right we have B star. On the right we have vertex T, left we have S, and all vertices in A star are reachable from S. So just consider any general case. So here just focus on edges crossing the boundary, because this way we define our cut. So our focus is on edges crossing the boundary between A star and B star. So something like this. V prime, and here we have V, and here we have U prime crossing . So just focus on this. So here consider this like so. By dotted arrow we show the edges in G, because in GF star there is no such edge, because you cannot reach starting from S any vertex in B star. So this dashed edge represents edge in G, not in GF star. So in GF star there is no such edge. So there are two possibilities we consider. So there is a directed edge from U to V in G, but it is not in GF star. So it means there is no forward edge. So first possibility, there is no forward edge. So this corresponds to no forward edge. No forward edge condition we know. So this implies you cannot increase the flow, means flow is full here. So flow is full means Fe is Ce. So here we have flow Fe is Ce. This is our first possibility. Similarly, second possibility we consider. So here we do not have any backward edge. So actually in G we have an edge from U prime to V prime. But in GF star there is no backward edge. So just apply the condition of not having backward edge. It means we cannot decrease the flow, means flow is 0. So for second case we have actually flow is 0. Here we have no backward edge. This implies flow is 0. So both cases we have considered. Now we consider what is value of the cut, and we compare the two. Just find the value of the flow. So just apply our earlier formula on that. Value of the flow is F out of A star minus F in of A star. So further we write this as sum of all Fe E out of A star minus sum of all Fe E into A star. So this is our formula for the flow. Now just simplify using our above observation. If E is out of A star, this is E is out of A star. What is value of the flow? Value of the flow is same as capacity. So first term becomes, you can write this as sum of all Ce E out of A star, and second term is 0. So there is no contribution from second term. So for incoming edges the flow is 0, minus 0. So this is exactly the definition of the cut A star B star. So we have proved that for Fulkerson algorithm the flow that we get is equal to the capacity of a cut, and just consider the inequality. Value of the flow is upper bounded by any value of the flow is upper bounded by any capacity of the cut. So this in itself proves that the Ford-Fulkerson algorithm gives maximum flow, and also using the same algorithm we can also compute the minimum cut. So just apply Ford-Fulkerson algorithm, find the maximum flow. Our cut will be set of all vertices reachable from S in the final residual graph GF. So just to find the time complexity of finding the cut, what extra time we require. So using Ford-Fulkerson algorithm, finding a min cut requires. So first Ford-Fulkerson algorithm in itself will require big O of Ce time, where constant C we define as this is sum of all capacity Ce E out of S, where S is the source node. So first we apply the Ford-Fulkerson algorithm, find the maximum flow, time complexity is big O of Ce. After that set A star equal to all vertices reachable from S. So this we can easily apply breadth first search or depth first search, and I have shown previously it again requires big O of E time. So making total contribution we get the same big O of Ce time. This is time complexity of finding minimum cut using the Ford-Fulkerson algorithm. So just the same example we consider, that the same simple example that we considered earlier. So I will not show again complete computation, just showing the final step of the Ford-Fulkerson algorithm that we studied in previous lecture. So last step, just showing the last step of Ford-Fulkerson algorithm. The flow that we get and the residual graph that we get. So flow F star that we get was like this: S, U, V and T capacities are 20, 10, 30, 10, 20. Flow I will show inside circles. Flow is 20, 10, 10, here also 10 and here 20. So this is the flow, and the residual graph we can make. The final residual graph that we get is like this: S, U, V and T. So we have backward edges of capacity 20, 10. So here we can see both capacities are full, so we cannot have forward edge, only backward edge. Backward edge equal to this value of the flow. Now here we have like this 20 and 10. So forward edge we can increase 10 up to 30. So the difference is 20. So forward edge has weight 20, backward edge value of the flow 10, that we can decrease. Then finally we have like this: backward edges 10 and 20, because flow is full here. So we cannot have forward edge, only backward edge value weight equal to value of the flow 10 and 20. So this is the final residual graph that we found using the Ford-Fulkerson algorithm. Now just to make the minimum cut, just apply the algorithm. Start with the vertex S and search for all vertices reachable from S. So here we can easily see there is no other vertex that is reachable from S. So the cut A star that we get is only S. The remaining we get is B. B star we get is UVT. UVT. So this is the minimum cut, and we can also find capacity of the minimum cut. This we have already computed before. Take a boundary around S. What are the capacities out? 20 plus 10. 20 plus 10 is 30. And what is value of the flow? Again, take S, boundary around S. See what is flow going out. 20, again 20 plus 10. Value of F star is also 20 plus 10 is 30. So here we can easily see that value of the flow is same as this we have already seen, and how we can generate the minimum cut using the Ford-Fulkerson algorithm. Any questions?